Alright friends, welcome back. In this video we're going to go ahead and take a day one for section 5.3 from your textbook, and we're going to continue to talk about logarithms here in this video, specifically we're going to be working with expressions involving logarithms and taking a look at how we can expand them and how we can condense them, okay? And so in order for us to be able to do any of that, we do need to kind of talk about three rules that you're going to be using as you do these problems here, okay? And so I want to go ahead and explain what these rules say and how to know them when you see them whenever you have examples of expressions to work with. Okay? And so let's go ahead and take a look at that first rule, right? So you notice that the same commonality between all of these rules is that they have a single log on the left-hand side. So what these rules are going to tell you is what you can substitute in the place of something that looks like what you've got written here, okay? So in your expression, if you've got something that looks like this, then we're always going to be able to substitute in its place what we're about to write down. Same thing, if you have something that looks like this, we're always going to be able to substitute in its place whatever we have on the right-hand side, and then same thing as we go through, we're always going to be able to make those substitutions here. And so what is equal to what? All right, well, in the case of that first one, I want you to notice that we're taking a single log of an input that looks like I'm multiplying two things, okay? So what I informally kind of refer to this as is the log of a multiplication, a times on the inside, okay? If you notice a times on the inside of a log, then what that's always going to be equal to, it turns out, is a addition on the outside, okay? So we're going to be adding two things whenever we notice that we have a multiplication on the inside, okay? Now what are we going to be adding? Well, these rules allow us to take a single log and break it up into the sum of two different logs, okay? So because I had a log base b from before, I'm going to go ahead and say here that I've got a log base b of something plus the log base b of something else. So these rules are pretty unique in that if it's a times on the inside, it's a plus on the outside, okay, between two logs. And so what are we taking the log base b of in these two situations? Well, we're just simply going ahead and referring back to what we were multiplying in the first place. So that'll be log base b of u plus log base b of v, okay? And so again, informally speaking, when I refer to this rule later on, you're going to hear me say a lot, if it's a times on the inside, it's going to be a plus on the outside between two logs. Okay, and so moving right along here in that next rule, we see here that that is going to be a division on the inside. And so you might guess if it's a times on the inside and then it's a plus on the outside, then you might go ahead and guess here that if it's a division on the inside, then it's going to be a subtraction on the outside, and you would be absolutely right in that assumption. So it is going to be a subtraction here, and very similar to the first rule, we're going to see that this is going to be the subtraction of two logs with the same base as what we started with. And the same rule applies here. We're just going to go ahead and do log base b of u and log base b of v. Okay, and so those first two rules are very, very similar to each other. They follow the same general pattern, and so those are pretty easy to remember. That last rule is a little bit of a unique one because you can see that I'm taking a single log of something that I'm raising to a power, a log of an exponential, you might say. And so this rule is pretty unique. What it basically allows us to do, and this is going to seem a little bit weird, but it's going to allow us to take that exponent and write it so that it's out in front of the log. Okay, and so that is going to be something that we could write as n times the log base b of u. Okay, so you might be wondering where all these rules come from and why they work. I'm not going to demonstrate that in this video, but the short answer is that remember that these log properties are all different language for being able to write exponents. And so we get all these properties for logs because of properties of exponents that we've already seen previously in the year. Okay, so what I'd like to do for the rest of the video here is I'd like to go ahead and demonstrate how you might go ahead and first expand an expression with a log in it, and then after that we'll take a look at some examples where we are condensing down. Okay, we're going to talk about a lot of examples in this video, so if you need to fast forward through certain examples or skip to certain ones later in the video, that is perfectly fine, but this is just one of those things where the more practice you get with it, the better you're going to be able to notice certain rules and be able to actually execute the problem here. So keeping these rules in mind, we're going to be on the lookout for anything when we're expanding that's going to clue us into how we can expand this to write this in a little bit of a longer way. So specifically speaking, if we are expanding, then we're going to specifically look out for what's on the left-hand side of these rules and see if we could trade them out for what's on the right-hand side as we go through here. So we're going to be looking for multiplications on the inside, divisions on the inside, and exponents on the inside as we go through. So if we take a look at this first example, one of the first things that jumps out to me in this expression that's on the inside of your log is the fact that we've got a big division going on, right? So we are dividing two things here, and so we can go ahead and rewrite that in the following way. If it's a division on the inside, then that means it's going to be a subtraction on the outside. So we'll say here the log base 2 minus the log base 2. Well, it's the log base 2 of what and what? Well, it's the log base 2 of whatever we had on top minus the log base 2 of whatever we had on bottom here. So in the top, we had simply a 7 times x to the third, and on bottom, we had simply a y. Okay? And so that's the first step of our expansion here. We may not necessarily be done after applying one rule. We have to look and see what we still have and decide if more rules can further be applied. And I think that's definitely the case here, and I emphasized this whenever I wrote it out. But if you look at that first log, we have the log of a product here, 7 times x to the third. And so remember that we have a rule that says if it's a multiplication on the inside, then it's going to be an addition on the outside. And so I could break up that first log into two logs. I could say that's going to be the log base 2 of 7 plus the log base 2 of x to the third. Okay? So that's pretty handy. And then, of course, we still have that minus log base 2 of y at the very end of our expression there. Okay? Now, you might be kind of asking yourself, like, okay, we just performed two rules. How do I get a sense for when I'm finished with the problem, right? Well, the idea is that you're going to look at all of the inputs to each log, okay? The input here is 7, the input here is x to the third, the input here is y. If any of those inputs look like a multiplication or a division, then we have a rule that tells us how to deal with that. If any of them look like we are raising something to a power, we also have that third rule that tells us how to deal with that. And so in this case here, if we look at that middle log, we have the log base 2 of x to the third. We have a rule that tells us what we can do with that exponent of 3 right here, and that rule tells us that we can go ahead and write that out in front. So we can go ahead and write this as log base 2 of 7 plus 3 log base 2 of x minus log base 2 of y. Okay? And now, again, we'll check each of our inputs. We've got 7, we've got x, and we've got y. None of those look like multiplications. None of those look like divisions. And none of them look like a number raised to a power. And so we know that we are all finished expanding this logarithm expression here. So that's going to be our final answer. Okay? So again, just kind of going back and reviewing here, you have to look at the input of your log and then look out for multiplications, divisions, and numbers raised to powers so that you can go ahead and apply those rules and expand this out. We're going to do a lot of examples here in this video, so again, like I said, feel free to skip around. Here in the next example here, we have log base 5 of the product of a bunch of things, right? So we have 25 times x to the 6th times y. And again, that is a bunch of multiplications on the inside of a log, and so we have that rule that says that we could break this up into a couple of different logs that are all being added, okay? And so we'll see here that that's going to be the log base 5 of 25 plus the log base 5 of x to the 6th plus log base 5 of y, okay? And so again, if it's a times on the inside, it's going to be a plus on the outside. There we go. Now, what I might encourage you to do now is just look at each one of your individual logs and then just decide if you can keep going with another one of your rules. If I look at that first log, one of the things that I notice here is that that's log base 5 of 25. And so if you remember what we talked about in the previous video when we introduced logs, we said that logs ask the question, how many copies of 5 multiply out to make 25, okay? Again, if it's been a while since that last video, then make sure to give that a rewatch. But that's the question that logs ask. How many 5s multiply to make 25? We know that it would take 2 copies of 5 to multiply to make 25. And so for that reason, the log base 5 of 25 is going to be the number 2, okay? So if you can simplify down your log with a nice, easy value like that, not a long, ugly decimal, then I would like you to go ahead and carry through with that. And we're going to follow up here with that plus. And now let's look at that second log here. We have log base 5 of x to the 6th. We have a number raised to a power there inside of our log, so we know what to do with that. We have that rule that says I can take that number 6 and I can write it out front. So that'll be 6 times the log base 5 of x. We're going to follow that up with plus, and then that final log there, it looks like the input on that log is just a y. That's not something that's a multiplication. That's not a division. That's not a number raised to any sort of specific power, not anyone besides 1 anyway. And so we're just going to leave that alone there. And that is actually the best that we're going to be able to do on that one. So 2 plus 6 times the log base 5 of x plus the log base 5 of y. That is the best we could do on that one. So we can see here that those were a couple of examples that were pretty straightforward. We had a couple of different little nuances in there as far as maybe simplifying a log, but applying the 3 rules that came above here, again, we are going in that direction from the left-hand sides to the right-hand sides as we go through. I want to kind of introduce you to some examples that maybe have a little bit of some subtle things we just need to keep track of here. So if you take a look at this next example here, one of the things that jumps out to me anyway is the fact that I'm taking the log of this big division. And we know exactly how to deal with division on the inside, right? We know that that's a subtraction on the outside. And so we're going to go ahead and write this as a log minus a log. So that is a log. Keep in mind, if you don't see the base, that's a common log or a base 10. It's just going to be the common log of the top, which says 9 times y, minus the common log of the bottom, which says 1,000 times x squared. Okay? And now we can obviously see here that we have some multiplications on the inside of our logs. We can go ahead and write those as additions. Okay? And so let's go ahead and carry through with that, right? So this first log is going to be split up into the common log of 9 plus the common log of y. There's really no fancy tricks or special things to look out for there. But when we move on to that second log, I want us to be a little bit careful because we are subtracting away that log, okay? So this quantity that we are subtracting off is going to have to be something that we go ahead and include in a set of parentheses so that we know to distribute in that minus sign here a little bit later on. So we are subtracting off this quantity, and we just need to make sure that whatever we substitute in the place of that quantity is something that's inside parentheses to tell us later that we have to distribute that negative inside, okay? And so let's go ahead and carry through with that. That'll be the log base 10 of 1,000 plus the log base 10 of x squared. And again, those parentheses are important here because, again, that minus sign that was in front, that is something that I do have to go through and distribute to both of these terms here, okay? And so let's go ahead and say here the common log of 9 plus the common log of y minus, and then let's think about these two logs individually in the parentheses here. So we have log of 1,000. Keep in mind, this is a log base 10, and so we ask that question, you know, how many copies of 10 multiply to make 1,000? That's the question that this log asks. And the answer to that question is 3. It's going to take 3 copies of 10 to multiply to make 1,000. And so that's why the log base 10 of 1,000 is simply just going to be 3, which I'll just go ahead and substitute in the place there. Distributing that negative to the second log there, we're going to have minus, and then what I want you to notice is that that log actually has an exponent on its input, and we can go ahead and write that input, or sorry, not that input, but that exponent out in front. We could say minus 2 times the log of x. And so now that we have everything written out here, again, we might just go through and just try to see if we're done by looking at all of the inputs and deciding if we're all finished up there. That is going to look pretty good. In the case of that first log where it says log of 9, that would give you a long ugly decimal because keep in mind the base of that log is a 10. And so the question that this asks would be how many copies of 10 multiply out to make 9? Well, we know not even a single copy of 10 multiplies out to make 9, so we know that that's going to be a long ugly decimal for us. So we're going to go ahead and leave that written as the log base 9, and this would be our answer for our expansion, just like that. So that one had a subtle different thing in it. That was a something that we had to go ahead and use some parentheses to make sure that we didn't mess up with any sign changes. Okay? And so here in the next example, we have a square root. And so I want to kind of show you what the deal is with this, right? So the first thing that jumps out to me, though, is just following along with our same classic rules here. We are taking the log base 5 of a division, okay? And we know exactly how to deal with that. If it's a division on the inside, it's going to be a subtraction of 2 logs on the outside, okay? And so we're going to go ahead and rewrite this as the log base 5 of the square root of 3x minus 5 minus the log base 5 of what we had in the bottom there, which is simply 7, okay? Now, taking a look at that second log there real quick, this log asks the question, how many copies of 5 multiply to make a 7? Well, we know not even a single copy or 2 copies of 5 would multiply to make a 7, so that's going to be some sort of ugly decimal number. And so we're just going to keep that as the log base 5 of 7. Turning our attention to the one that came before it, though, we obviously have this to figure out, right? So how do we do a log of a square root? Well, back in the day, whenever we first went over our exponent rules, one of the things that we talked about is how to convert a root into an exponent. So we had this rule right here. If we ever took the nth root of a number, like say a, this is always equal to that number a to the power of 1 over n. Okay, and so that is always how we dealt with radicals and converting them to exponents, is we went ahead and we followed this rule. So this might have to be a rule that you write down in your notes somewhere and keep track of, because if you ever have a log of a radical, this is exactly the way that we're going to handle that. We're going to take that square root. The index of that square root, of course, is a 2, and so that's playing the role of n up there in the rule. And so we're just going to go ahead and rewrite that first log as the log base 5 of 3x minus 5 to the power of 1/2. Okay, and then we're simply going to say minus the log base 5 of 7 that we had there. Okay, and the reason that that helps is because now we are allowed to go ahead and take this exponent and apply our exponent rules for logs and write that out front. So that's going to be 1/2 times the log base 5 of 3x minus 5 minus the log base 5 of 7. Okay, and now if you look at that and ask yourself if you can continue, if you can keep going, again, you're going to look at the inputs as you make that decision. We already decided there was nothing to do with that second log, but in this first log we have this as an input, 3x minus 5. And the reason that we're not able to do anything with that is because we don't have any rules that tell us what to do with a subtraction on the inside of a log. We have rules for multiplications and divisions inside of the log, but not subtractions inside of the log. And so, as weird as it might seem, we're actually just going to go ahead and box that as our result for the expansion of this expression, okay? And so I wanted to present this example to you as just a way to kind of demonstrate that sometimes square roots are going to come up, and we need to know how to deal with those. As the last example for expansion, let's go ahead and take a look at part E here, where we're taking the natural log of the square root of x squared divided by y. Okay. The first thing that we're going to do is we're going to get rid of that square root, and we of course are going to do that using the exact same rule that we just discussed. And so that is going to be the natural log of our input x squared divided by y, all to the power of 1/2. Okay. Again, converting a root to a fraction exponent is something very, very important. It's going to allow you to go ahead and do these problems really easily, because now that we have the log of something to an exponent, we can go ahead and follow that exponent rule for logs and write that exponent out front as a coefficient there. So we're going to have 1/2 times the natural log of x squared divided by y. Okay. The next thing that you will want to notice is that you are taking the log of a division, and so if it's a division on the outside, we know that that's going to be a subtraction between two logs on the outside here. So that's going to be the natural log of what's on top, x squared, minus the natural log of what's on bottom, which is y. Now, one point that I do want to make here is what to do with that 1/2 that's out in front, right? This is another case where 1/2 was being multiplied times this quantity right here. And what you just did is you substituted that out for this, this difference right here. And this is all something that's being multiplied by 1/2. And so the way that we would continue is we would just want to go ahead and distribute that 1/2 inside after we do just one more step. And that one more step would be to go ahead and clean up any of the logs that we have inside of the parentheses here. If you take a look at that second log, that's just the natural log of y, nothing to really do there. But if you take a look at that first log, that's going to be one that we can apply our exponent rule to. And so we could put that number out front, in which case we can see here that we're going to have 1/2 times 2 times the natural log of x minus the natural log of y. And now we can go ahead and distribute that 1/2 back inside. And so 1/2 times 2 is actually just going to make 1. And so that's going to leave us with the natural log of x minus 1/2 the natural log of y. And that will complete the problem. There is the expansion for that expression involving logs. Okay? So again, you might be able to develop an appreciation for why we call this expansion. We're taking an expression that only involves a single logarithm, and we are rewriting it in terms of a combination of a bunch of different logarithms here. And so, again, the direction when using our rules whenever you're expanding is to go in this direction right here, from the left-hand side where everything is condensed over to the right-hand side where everything has been expanded out. However, if we are going to go ahead and do the reverse direction of this, then we are going to go ahead and reverse our direction of what we are focusing on. And so whenever we condense, which is what we're about to do, we're going to start off with a bunch of expressions that look like this, and then we're going to go ahead and substitute in their place something that looks like what you see over on the left-hand side of these rules, okay? And also, we're going to perform them in the reverse order. So the first thing that we're going to look at whenever we are condensing is we're going to look for some numbers out front. If you have any numbers in front of your log, that's something that you can always go ahead and write as an exponent, and then after that we're going to be on the lookout for plus and minus signs and then condense those down a little bit further. So you're going to find that when you condense, there's a little bit of the opposite thinking that you're going to need to do in order to make some sense out of that. But let's go ahead and take a look here at example 2 where it does say to condense the expression, and we're just going to go ahead and keep in mind some of those same rules that we talked about before and think about them in the reverse order here as well. So the first thing that you're going to look out for, of course, are any numbers in front of your logs. Here I have 3 different logs, and I only have a number in front of this second one here. And so I can go ahead and apply the exponent rule here and work backwards and say if I've got a 2 that's out in front, then I can go ahead and make that an exponent on that input of 2. In which case that log in the middle is going to look like log of 2 squared, and we actually know what 2 squared is. We know that that's going to be the log of 4, okay? And so whenever you go ahead and continue to write out this expression, we're going to go ahead and say that that's log of 6 plus the log of 4 minus the log of 3. Okay, now how do we continue? Well, you know that you're going to be finished whenever you condense this down into a single log, or you've done as much as you possibly can, right? And so we do see that we have a plus sign and a minus sign here, and it kind of begs the question, you know, which one of these are we going to perform first? The answer to that question is whatever comes first as you read from left to right. We always read books and different sentences in English from left to right. It's the exact same thing with math expressions. And so the first thing that comes from left to right is going to be this plus, and so we're going to go ahead and handle condensing this down first and then move on to that minus log of 3 later. And so we know that if it's a plus on the outside, that means it's going to be a multiplication on the inside. And so we're going to go ahead and condense this down to log of 6 times 4, and we know what 6 times 4 is. That is simply just 24. So that's going to be the log of 24 minus the log of 3. Okay, and so now that you have that condensed down, we will now go ahead and pick up here with this minus in between these 2 separate logs here. If it's a minus on the outside, it's going to be a division on the inside here. And so we can just go ahead and continue here. I'm going to try not to spill over into my next problem, but that's going to be the log of 24 divided by 3. Okay, that's again just applying our division rule to that. And we obviously know what 24 divided by 3 is going to be. That's going to be 8. So we condense this down into the log of 8. And that is about as far down as we can condense that expression that we started with. So again, we're working the opposite direction of what we just did with expanding. We are going to take a look at our rules in the reverse order and apply one at a time until we get down to a nice single logarithm. Okay? Here in this next example, we have the subtraction of 2 logs, but again, we have some numbers that are out front, so we're going to take care of those first. So this number of 2 and this number of 5, we're going to go ahead and write those as exponents on our inputs. And so this is going to be the log of 7 to the power of 2 minus the natural log of x to the power of 5. And again, 7 to the power of 2 is something that we do know how to evaluate. That's just simply going to be 49. So we're going to say the log of 49 minus the natural log of x to the 5th. And now you might ask yourself, you know, how do we keep going, right? Well, the problem here is that I've got the log base 10, that's the common log, of 49, minus the log base e, that's the natural log, of x to the 5th. Our rules do specifically say that the bases of our logs need to be the exact same in order for us to go ahead and apply the rules. And so for that reason, we're kind of hitting a wall here. We can't really continue any further beyond this point because the bases of our logs are different, okay? And so we aren't going to be able to do anything else with this one. And I might just make the note here to just be on the lookout for different bases. If we do have different bases, that's going to have to be one of those things where we have to say that we cannot continue with the rules that we just discussed. The next example is something that I've already gone ahead and done out for the sake of time here, and one of the things that I want to kind of focus on here is how to do the problem in a little bit of an easier way, because if you look at the statement of the problem at the very beginning, you do have a bunch of minus signs. We always have to be careful whenever we have minus signs in the mix because minuses have a specific order to them. We do have to kind of be careful here. So one of the things that you see me doing here is you notice that I'm factoring out a negative, okay? So I'll even make a note there, factor out a negative from the second and the third logs that you've got. If you do that, it creates a little bit of an easier way to do the problem because what you have here is some leftovers that leave behind a plus in the middle, and we know how to deal with that, right? It's a plus on the outside that's going to convert to a multiplication on the inside. And so you can see how the rest of that work shakes out there in the usual way. I just want to go ahead and do one last example here for the video. Again, I know it's a long one, so thank you for bearing with me. But let's go ahead and take care of this last example here where we have a bunch of natural logs and we have some fractions that are in front of our logs here. So again, the way that we always begin is we go ahead and we take care of these numbers that are in front. And so I got some fraction numbers there. I also have the number 4. We know how to deal with these. These just become exponents on our input. Okay, and so we can go ahead and write this out as the natural log of x to the power of 1/4 plus the natural log of y to the power of 3/2 plus the natural log of z to the power of 4. Okay, now as we continue to go through here, what we might just go ahead and do is notice that we've got some fraction exponents. These are things that we can always trade out for the radical way of writing them. Okay, so I'm going to go ahead and do that at this time. So that's going to be the natural log of the 4th root of x plus the natural log of, and keep in mind the number on bottom of the fraction, that's always the index of the root. And so because the number on bottom in that second log is a 2 in the exponent, that's going to mean I'm going to have a square root. So that's going to be the natural log of the square root of y cubed, and then plus here the natural log of z to the 4th. Okay, and so now continuing, we notice that we have a bunch of plus signs, and of course we go ahead and handle the first one that pops up as we read from left to right, and so that's going to be condensing these first 2 logs down. And so we can go ahead and do that by saying that if it's a plus on the outside, it's a multiplication on the inside. And so we're going to go ahead and handle that by saying the natural log of the 4th root of x times the square root of y to the 3rd. Okay, and we're going to say here plus the natural log of z to the 4th. Okay, and we can go ahead and continue to further simplify this log down by saying here that that's a plus on the outside yet again. So I can go ahead and condense these 2 separate logs into the same log by simply saying the natural log of the 4th root of x times the square root of y to the 3rd times z to the 4th. Okay, and that is the best job that we can do as far as simplifying that log down as far as it'll go. We've condensed that into a single logarithm, and so that is about as good as we're going to be able to do on a problem like that. Okay, and so that's all I have for this video. Again, just kind of taking a look at some of those rules and thinking about what direction that you're going in, whether you are expanding or condensing. We're going to be using the same exact rules in each one of these cases, but we're going to kind of have to think about the order that we apply those rules in. So I hope that everything has made sense here. Thank you very much for your attention, and I will speak to you guys in the next one.